University Video Communications, with the sponsorship of Schlumberger Laboratory for Computer Science, welcomes you to this edition of the Distinguished Lecture Series, Leaders in Computer Science and Electrical Engineering. Today's presentation is Automated Program Synthesis. The goal of automated program synthesis is to bridge the gap between what is easy for people to describe and what is possible to execute on a computer. This talk will summarize the state of the art and provide examples from a specialized system that generates FORTRAN and C code for mathematical modeling. Our speaker, Elaine Kant, received her PhD from Stanford University, taught at Carnegie Mellon University, and is presently program leader of the Design Environments Group at the Schlumberger Laboratory for Computer Science. Her research interests include supporting scientific problem solving, as well as understanding and automating the design, implementation, and analysis of algorithms and programs. Elaine Kant.
The animation sequence you are looking at uses data from a sonic wave propagation program. Such animations help mathematical modelers design new measurement tools to locate hydrocarbons in oil wells. What's interesting about the program is that it was automatically generated by a program synthesis system. This system, called Synapse, was developed at the Schlumberger Laboratory for Computer Science. Schlumberger currently spends $5 to $10 million annually to write mathematical modeling software. Automated program synthesis could potentially save us millions of dollars and generate additional revenue by helping get products to market more quickly. Automated program synthesis is a dream that's been around as long as there have been computers. Progress continues to be made, but expectations rise even faster. No completely general program synthesis systems exist, but hundreds of sites are using spin-offs of the technology, such as very high-level prototyping languages, and more places are developing application-specific program synthesis systems. Example applications include telecommunication services, software language translators, VLSI router algorithms, and mathematical modeling. Although synthesized systems are not yet in common use, these are not toy systems. The rule compiler for the most widely used system, Refine, is written in the system's very high-level language and synthesizes an efficient version of itself by bootstrapping. The entire family of Refine tools is several hundred thousands of lines of high-level language source code. In this talk, I will define what I mean by automated program synthesis, give some examples of what it can do, outline the basic approaches to program specification and automated implementation, and then discuss some additional topics for research in the state of the art in practice. First, let's consider the problem. Software is notoriously hard to write in time and to budget. Program synthesis does not address the project management issues of coordinating groups of people, but it does increase the amount of work one person can do and facilitates formalizing and recording important design decisions. Some difficulties in software engineering arise from evolution of specifications. Although program synthesis cannot prevent changes in the hardware and software environment or changes in the user's desires, it can help with other problems. For example, if application knowledge is in machine understandable form, then some of the problems due to programmers having to learn the application can be avoided. If a problem is described in application terms, it's easier to find any existing related specifications to start from and easier to check specification validity. In addition, the spread of information caused by optimization conflicts with the need for localized design information when making changes. When programs are automatically synthesized, it's much easier to record the design and optimization decisions and then make changes by modifying the specification and re-implementing the program, reusing most of the recorded decisions. So we see that program synthesis allows us to reuse several types of abstractions. Abstractions of application concepts, abstractions of programming constructs, and abstractions of design strategies. With this background, let's try to define program synthesis. Program synthesis is the process of bridging the communication gap between a human and a computer to achieve an arbitrary computational task with as little human decision-making as the user desires. Ideally, the user can specify a problem in terms natural to the application domain, reducing the cognitive distance from the user to the specification. The specification language should enable concise description of the functional behavior and constraints of the desired task without requiring details about the computational model of the implementation. Unfortunately, reducing the distance to the user may increase the distance to an executable specification. Traditionally, program synthesis is a translation of a high-level specification into an efficient target language program. But because high level is relative to current practice, automatic programming is a moving target. For example, in the 1950s, FORTRAN compilers and even assemblers were called automatic programming systems. But at that time, people had to do most of the work in making programs closer to the machine's languages. Today's very high-level languages are moving closer to the way people think, but there's still a big gap. One compromise we can make is to specialize the communication language to a particular application domain, achieving power at the expense of generality, a common trade-off familiar in artificial intelligence. Another area of compromise is automation. Unlike most existing compilers, a fully automated synthesis system must make many choices among the algorithms, data representations, and optimizations. No algorithmic decision-making techniques exist, and search and performance analysis are expensive, so sometimes the user may make the choices. Later, I'll elaborate on the trade-offs made by various techniques. But first, let's look at the benefits and costs of building a program synthesis system, and then look at an example. The continued interest in program synthesis is due to its potential benefits. In the ideal system, programs would be easy to specify in terms natural to the end user. The automated implementation would prevent careless errors. Programs could be optimized for different target machines and programming languages simply by changing the specification. The clarity of the specifications and the formalization of programming and application knowledge would facilitate modification and reuse. Overall, since the user could quickly experiment with different specifications and implementations, productivity would be dramatically increased. Of course, achieving these ideals is very expensive. Although programming knowledge is fairly formal and many abstractions have been identified, there's no general agreement on the proper representations, so it requires major effort to codify programming knowledge for a new system. Secondly, it's a very large investment to analyze, abstract, and codify a new application domain. There are gaps in our knowledge of useful abstractions to map even the lowest level of the application onto computational models. In addition, it's hard to select the boundaries of application and programming knowledge and to select the grain size. Too small a scale of abstractions increases the difficulty of decision making. Too large a granularity makes it harder to reuse the abstractions. We must also consider the costs of maintaining the synthesis system and availability on different platforms. The specifications in design history are much less useful for evolution without the automated system to implement them. Other costs are code efficiency that may not be as high as the best human-produced code, and added complexity in debugging programs with automatically generated refinements and optimizations. Finally, the availability and training of people to carry out the domain analysis, system building, and problem specification must be considered. As in any cost-benefit analysis, the overall economics of buying, augmenting, or building a synthesis system must be compared to the costs of bringing hand-coded software to market in time and cheaply enough to make money. For most users today, the costs of synthesis are too high. Only a few pioneers are making the investment in tools to amortize the cost for future users. In general, program synthesis only makes sense if your application area is used frequently, either because many similar systems are written or because one system is modified frequently to determine the desired specification. The domain should lend itself to natural, concise specifications, and experts in the domain should agree on the fundamental primitives, basic building blocks, and generic architectures for solutions. The solution technique should be well understood, with standardized control and data abstractions that lead to automatable transformations. Checking for patterns in existing source code is one way to predict this. Finally, the domain should be complex enough that there's a payoff to speeding up the implementation process. One situation in which we think program synthesis will pay off is reducing the amount of time and money that Schlumberger spends on mathematical modeling. In applications such as analyzing data to find oil and gas, or in designing commercial and residential utility meters, automating the coding of models could save millions annually and reduce development time. In particular, finite difference algorithms are quite common in Schlumberger's modeling applications. The problems can be summarized in about a page, but typically take 20 or more pages to implement. The basic algorithms are well described in journals. Because models must be run on gigabyte-sized data sets, the speed of target code is very important. The new parallel computers permit three-dimensional modeling, which was not feasible previously, but 3D codes have even more long arithmetic expressions and boundary conditions. This presents us with the opportunity to free the modelers from hand-coding many error-prone details and from learning the intricacies of new architectures. We believe an application-specific synthesis system can be developed more quickly than any generic tools for parallel programming. Our Synapse program synthesis system is being developed to address this opportunity. For example, a 2D problem can be specified to the system in 60 lines and generates about 1,400 lines of FORTRAN in 2 minutes on a Sun 4. More complex 3D examples can take up to 10 minutes to generate 5,000 lines of connection machine FORTRAN. Such code could take weeks to generate by hand. And in cases where we've been able to make direct comparisons, the synthesized code is slightly better than moderately optimized hand-generated FORTRAN 77 code. On the cost side of this equation, several person-years of effort have gone into building the Synapse system, and it's currently limited to finite difference algorithms primarily. The code that we generate for the connection machine is not yet as well optimized as the code for sequential machines. Let's consider a specification for a finite difference algorithm to model seismic wave propagation. Here's how you might describe the problem to a colleague. The 5 equations on the next 2 slides define an elastic wave propagation problem by relating stress S and particle velocity u in a solid material. The problem is to compute sampled values of S and u for a wave field traveling through the material. Elastic properties represented by coefficients such as rho determine the wave velocities. The region is a rectangular prism with absorbing boundaries. Initially, the region is at rest, then an explosive source of stress is applied to one point. We want to use a finite difference algorithm to compute the sampled values and implement the boundary as an extra region filled with absorbing material. We've tried to model the choices in our representation after such a natural description. This figure indicates some of the choices made in our example that determine first the problem description in terms of equation formulation and boundary type, then the specific mathematical model, and then the algorithm details. Not shown are programming choices such as how to represent data. Here's the specification given to the Synapse system for this program. The first part is the problem formulation. The equations were not all written out by the user, but were generated from the specification of a stress-strain model type and a set of coefficients. If we want to change to a 3D model, we simply add another value y to the dimensions. The system then automatically adjusts the equations to compensate. The remainder of the specification is a description of the solution technique, an explicit finite difference algorithm with a 4th-order approximation, staggering of the grids, and a taper for the absorbing boundary. The specification and design decisions can also be made interactively. The system applies heuristics to make the choice, but the user can inspect these choices or force an eliminated choice. For example, the heuristic applied here restricts the equation formulation based on the problem domain, so the user does not have to select from the complete set, which is larger than shown here. Next, let's look at some simplified versions of the rules that Synapse applies to synthesize this example. The first rule shows how to approximate an equation for computing a physical quantity, such as stress or particle velocity. The rule recognizes derivatives in the equation and replaces each one with a discretization computed by another rule. There are actually a set of discretization rules that the system must choose between. It makes the choice based on whether or not certain symmetry conditions exist, and then applies the selected discretization. Here we see one such rule that constructs a difference expression by finding the order of approximation, the evaluation point, and the name of the discrete variable. Sum the expressions with the continuous variables of the derivatives replaced by offset variables. From this specification, Synapse generates several thousand lines of FORTRAN. We run this code on inputs suggested by the end user to produce data files for wave fields at a sequence of points in time. We fed these data files to a Silicon Graphics program to generate the following animation sequence. This is a two-dimensional simulation of a seismic wave propagating through 4 different materials shown in different shades of blue. Because the wave travels at different speeds in the different materials, some of the energy is reflected and some is transmitted. In this repetition, notice that the borders between the materials are angled and there's a fault line, which breaks up the symmetry of the waves. The simulation uses a 400 by 400 grid with absorbing boundaries. Synapse has been used to synthesize several dozen programs in FORTRAN 77, C, and connection machine FORTRAN. Most applications involve seismic and sonic wave propagation using finite difference algorithms, but we've also looked at heat diffusion and a deconvolution problem optimized with Fourier transforms. Our examples are all in the neighborhood of a page of specification, a 5 to 20 size expansion factor for the implementation, and minutes for synthesis time. Synapse is implemented in Mathematica, which provides a powerful programming language with rules, pattern matching, and algebraic simplification. We also chose Mathematica because it's available on virtually all platforms used by engineers and is useful for both symbolic and numeric reasoning even without the Synapse system. Now let's go back to the basic techniques of program synthesis. We'll first review the framework, then look at some specification styles, implementation techniques, and knowledge representations. The main focus of program synthesis is translating a specification into an implementation. However, the specification language itself obviously affects what can be specified and implemented, and executing the resulting program may indicate changes needed in the specification or implementation. So there must be feedback loops between all phases based on analysis of the results. Transforming a program description into code may take several intermediate levels, though not necessarily in the nice linear order shown here. Think of each level as an abstract machine with several components we'll call domains of knowledge, each of which may have its own vocabulary. For example, from a program description in terms of models about wave propagation, we derive, through domain knowledge, a more complete specification expressed in terms of partial differential equations, data input descriptors, and graphical outputs. The targeting to a particular architecture, such as serial or parallel, and elaboration to the abstract algorithm level require formulation in terms of concepts such as difference expressions and regions on a grid. These domains are further refined and optimized to construct a generic program with concepts such as array ranges and numerical analysis routines. Finally, detailed target language knowledge helps translate the program into code in FORTRAN or C. The most appropriate reasoning techniques for making the transitions may also vary with the level. In going from problem description to specification, user input and general problem-solving methods such as opportunistic search are appropriate. In going from specification to algorithm, theorem proving and backward chaining are sufficiently general methods, but given enough application knowledge, forward chaining will be more efficient. Forward rule applications will generally handle the transition from design to generic program description. The translation to code is easily accomplished with simple parsing and syntax tables. Using many different methods in combination is expensive in terms both of building a synthesis system and generating a particular program. Compromising on one or two simple methods, such as forward chaining, is much more practical. Now let's look at some specification techniques. Here's a rating of techniques against some goodness criteria of being expressive, executable, and so on. Don't take the table too literally. The techniques represent broad classes, and many subjective factors go into each rating. Specification by natural language or by examples of input-output pairs, such as 1, 2, 3 goes to 3, 2, 1, are appealing techniques because of the convenience to users. Unfortunately, both techniques often lead to ambiguous specifications. Specific examples must be generalized, and there may not be a unique generalization. For instance, it would be extremely verbose and uninformative to give examples of 3D input and output arrays for animation sequences and wave propagation problems. Because natural language and example specifications are so far away from an executable language and can apply to arbitrary applications, no one has yet developed general implementation techniques. A variation of the examples technique is giving traces of behavior. This is useful in applications such as specifying and implementing the user view of telephone protocols. The appeal of natural language is not only the language aspect, but also that it's knowledge-based and involves dialogue. Word meanings are concepts shared between the user and the system. In a sense, natural language is a combination of application-specific languages. Also, dialogue enables the user to give an initially incomplete specification and have the system come back with questions. Such interaction is also possible with other techniques if the system shares enough knowledge with the user to notice when parts of the specification are missing and communicate what more is needed. Formal specifications use logic or algebraic types to express the relationship between program inputs and outputs. These specifications have the virtues of being unambiguous, high-level, and expressive, given the right axiom sets or domain theories. Although some people find formal specifications easy to write and understand, some people who would be end users of a system do not. And unfortunately, unless a good deal of application-specific guidance is provided to the system, implementing from these specifications is usually very time-consuming. Formal specifications are therefore most useful if reliability is critical to the application, such as a medical application or emergency prevention system. Very high-level languages are closer to machine code than our natural languages or examples, but they're more expressive than current programming languages. They include specific, powerful computational models, such as databases, finite state machines, object-oriented messages and hierarchies, declarative constraints, and state descriptions with non-determinism in future behaviors. Still, very high-level languages are basically programming languages and may be difficult for non-programmers to understand and write. Thus, it should be easy to add application-specific extensions. Some people define these languages as executable specifications, which means it's easy to get implementations, although not necessarily optimized ones. However, languages that include constructs such as references to future values are quite difficult to implement. Because of the difficulty in implementing all high-level constructs, and because the user may want to specify some design details, people have developed wide-spectrum languages that include constructs ranging from application level to low-level details. Including low-level constructs in a specification makes it harder to read, but it's convenient for a synthesis system to have a uniform syntax for gradually introducing more implementation commitments into an internal representation. The application-specific approach has been most successful in well-understood and widely used domains. For example, there are programming applications such as parsers, structure editors, finite state machines, and communication protocols, and business applications such as database queries, report generation, financial analysis, and display screen creation. Sometimes these languages are just collections of values for parameters to subroutines, but sometimes the user inputs a graphical flow diagram or provides a formal language description. Application-specific languages, by definition, should be expressive and understandable for the intended domain, but they may be completely unexpressive outside that field. If an application is well understood, implementation of a code generator is usually practical. Let's turn now to implementation techniques. The goals are to produce correct and efficient code for any general but sensible specification reasonably quickly and with as much automation as the user desires. Implementation is hard because the goals of efficiency and correctness lead to complex synthesis processes and may conflict with the goals of generality, speed, and automation. To guarantee correctness, the semantic conditions on implementations must be determined in advance and checked at runtime. However, this is not always feasible or desirable. For example, to prove correctness about scientific programs involving numerical approximation, we'd have to codify and extend the whole field of numerical analysis. But in many cases, people want to use the programs to determine experimentally which algorithms give the best approximations. To produce efficient programs, a synthesis system must be able to generate many choices of data structures, operations, and algorithms. Deciding which of these to combine to produce the most efficient code could require searching through the space of alternatives and analyzing each. The search and analysis necessary for correctness and efficiency slow the synthesis process, which conflicts with the goal of fast code generation. This can be partially remedied either by forcing the user to make all the choices, which conflicts with the goal of automation, or by pre-analysis of the choices and addition of situation-specific heuristics and evaluation functions, which isn't completely in the spirit of generality. Approaches to program synthesis differ in how they address the trade-offs between generality, speed, and automation. One interesting reality check is the number of users. This curve gives a very approximate count of the number of sites using each technology. The most prevalent tools are those that require the user to supply the knowledge, such as compilers or case tools. Also fairly widespread are some of the early application generators, which were hard-coded and specialized to applications such as database queries. A newer trend is to use prototyping languages or very high-level languages to write more extensible domain-specific program generation systems for smaller numbers of users. Other techniques are still in the research stage. The same placement of techniques on this curve could be used with different scales to illustrate the number of lines of code produced and the generality of the system. However, some less desirable properties also tend to follow this curve, such as the size of the specification and amount of human effort substituted for automation. This is why these techniques are of interest. So now let's look at each of these implementation techniques in a little more detail. Compiler technology compromises by having the user provide the domain and algorithm knowledge in the program. Few decisions or non-local optimizations are made. Optimizing compilers sometimes compromise on automation by having the user provide pragmas that tell the compiler what to do. Compilers for very high-level languages do make some interesting choices, but tend to be hard to modify. An example of a successful use of this technology was the SetL synthesis of an Ada compiler. It was better than the early handcrafted Ada compilers, but not as good as some recent ones. Case tools support the user in defining modular structure and provide conveniences for graphically defining input-output relationships and declarations. However, there's no specification other than the series of module elaborations that the user manually supplies. So-called case code generators simply paste together a text form translation of the module interconnections and declarations with user-supplied code bodies. Since case tools don't provide any refinements or do any optimization, they aren't true program synthesis systems. Application program generators are often special-purpose compilers. They compromise on generality by limiting themselves to narrow domain and sometimes sacrifice efficiency by producing code that must be interpreted. For example, problems typically involve repetition by implicit iteration. Implementation may be through database calls, tables, or repeated code lines. Application generators do enable the reuse of designs. But in early systems, the abstractions were often inaccessible and buried in the code of the generator. Rule-based technology can usually achieve the same goals in a more general way. Transformational implementation is the stepwise refinement of a specification into target language-only constructs. The correctness of individual programs is assumed to follow from the correctness of the individual rules. The transformation rules refine or optimize constructs after testing applicability conditions. Compared to application generators, the transformational approach encodes knowledge in more disciplined and factored style. This factorization makes the knowledge more combinable and therefore more reusable, and makes it easier to add new knowledge. However, more choices exist, so more knowledge about decision-making is needed. There are two subclasses of transformations. Knowledge-based systems have large-grained rules engineered for particular applications or models of computation. More formal systems tend to have a minimal set of general rules from which larger-grained rules can be derived. The formal approaches are more concerned with guaranteeing correctness and formalizing optimization techniques, while knowledge-based approaches try to quickly generate larger programs for end users. Knowledge-based techniques usually implement very high-level language or application-dependent specifications. They have proved useful for applications such as mathematical modeling, translations from logic formalisms to database queries, and translation between conventional languages and dialects. A related application is recovery of design information from code. First steps towards this are the backward application of forward synthesis rules. Formal rule-based approaches usually work on optimizing small but complex algorithms. They typically use small numbers of very general transformations, such as replacing a function call by its body and vice versa. Simplification rules are also applied. A typical series of steps is to remove nondeterminism, replace recursion with applicative constructs, eliminate intermediate list structures, and finally produce imperative code. Techniques for extending and combining abstract data types are important research topics. Another class of formal approaches generates programs by finding a constructive proof that the outputs satisfy any inputs that match the preconditions. The proofs are constructive in the sense that a case analysis in the proof turns into a conditional in the program. The output programs are usually compositions of applicative functions. Large search spaces were a problem in the original proof approaches such as resolution, so researchers are looking for better formalisms and proof techniques to help localize knowledge and speed up search. For example, knowledge-based search control strategies seem promising. Meanwhile, users provide the control via different sets of axioms, lemmas, and proof schemas. Another approach to generality is to use AI problem-solving methods such as analogy or symbolic evaluation to replace explicit codification of knowledge by systems with more creativity. Unfortunately, this usually reduces the speed of program generation fairly drastically. Techniques such as learning by chunking aim to reduce search and program generation time. If efficiency of the application is not critical, an expert system approach that solves individual problems without even creating a program may be appropriate. There's still a need for good research in logic-based and AI problem-solving approaches, but to me, the most practical technology for the next few years is knowledge-based transformations. This approach yields systems that can generate interesting programs and provide realistic examples to help determine which research areas are most important. Now let's look at some different types of knowledge and their representations. To illustrate the general concepts, I'll use some simplified versions of examples from the Synapse system with Mathematica-style notation. 3 basic types of information are required for each domain: a theory of domain objects and operations, a theory of program schemas for implementing high-level constructs, and design strategies for guiding the synthesis process. Domain theories are the basic building blocks of a system. They should be like abstract data types in that each domain has a vocabulary of objects and operations, some attributes of and relationships between objects and operations, and semantic integrity requirements defining legal compositions. A program schema is a plan structure that tells how to instantiate an operation or how to elaborate a data object. Often a schema composes bigger, more detailed pieces out of smaller ones. A design strategy is an overall guideline for putting together a subsystem. It encapsulates the high-level goals, choices of plans to achieve the goals, and ways for deciding between the alternatives. An example of a domain theory is the one shown here for mathematical modeling. This is a domain at the problem formulation level. It uses definitions from other domains, time and space and physical quantities. Objects in this domain include geometries, which map space to material properties, and mathematical models, which map geometries, space, and time to physical quantities. Operations on model objects include computing steady-state values for quantities, doing forward modeling by computing quantities that change over time, and interpretation, an inverse operation computing geometries from physical quantities. Constraints include ensuring that measurement units of parameters to modeling operations match. Another domain at the formal specification level is that of partial differential equations, or PDEs. Objects here include equations and derivatives. Operations include normalizing equations, computing dependencies between variables, and solving sets of equations. The goal in defining an architecture of domain theories below the algorithm level is usually that the theory should correspond to abstractions that are independently implementable. The constructs in a high-level theory correspond to the goals of implementing them independently at lower levels. If the interfaces are standardized with the same attributes and operations for all the refinements and alternatives, then decision-making and instantiation are simplified. The bigger and more independent the blocks, the more practical and efficient the synthesis system. At higher problem and algorithm levels, reformulation of the whole conceptualization may also be appropriate. In designing individual theories, the usual concerns of abstraction should be addressed. It should be clear what the user can vary and what is fixed, what is hidden, and what can be reused. The second type of synthesis information is the program schema, which can be any plan to achieve a set of objectives. A common type of plan is the refinement schema, which tells how to move between domains by substituting more concrete constructs for the more abstract constructs at a higher level. For example, our problem description begins as the application of a forward model to a set of PDEs in space. After we decide to use the finite difference technique, we elaborate the algorithm by refining the PDEs into discrete form. Then we determine a partial order for evaluating them and discretize the spatial constructs into a grid. Eventually, we refine the solution into loops over arithmetic expressions at array locations. By the end, all the application-specific constructs have been refined and only executable constructs remain. In our example, we loop through regions and update the quantities according to methods associated with regions. The normal method is to discretize by finding an equation for a region and calling the approximate rules we saw at the beginning of this task. For example, if we have this input and approximate calls this discretize rule, then here's what the refinement process produces. Another type of schema is the source-to-source transformation, which reformulates problems within one domain. At the problem specification level, these transformations may produce more understandable and easily solvable representations. For example, applying Fourier transforms may greatly simplify a problem. At executable levels, the purpose is optimization of the target code. One class of synapse optimizations is specializing array representations, such as using a diagonal array. Optimization rules in Synapse make frequent use of conditional propagation and expression simplification, a few simple versions of which are shown here. Some simplifications we wrote explicitly for Synapse, but many others were already part of Mathematica. The effect of the target architectures can be seen both during refinement of the algorithm and later during optimization. Here we see that an absorbing taper boundary can be expressed as the product of three conditional expressions. On a memory-poor architecture, the implementation becomes a set of separate loops for each boundary region. On a massively parallel architecture with enough memory, it's more efficient to write one uniform array multiplication. Most of the refinement we just saw went along smoothly because Synapse's design strategies are organized to make an initial set of choices and then minimize later interaction. In general, a design strategy has a goal that it achieves, a set of alternative plans to satisfy the goal, and a method for choosing between alternatives. If alternatives are not directly associated with the goal, there must be a way to find them. Logic systems often use unification, whereas rule-based systems use pattern matching. Let's look at some example design strategies in Synapse. The plan for defining a problem, represented as a declarative task sequence, is to identify the application domain and model type to help set up the equations. The design strategy for the first task has the goal of selecting the application domain and a set of stored alternatives, and uses the default selection method of asking the user to choose from the alternatives. After the problem is specified, the system can make more of the choices automatically. For example, the best method to achieve the goal of finding the model type depends on the domain. If nothing specific is known about the domain, the user will be asked directly for a list of equations. Or if the domain is a known one such as wave propagation, more specific techniques are available. The decision-making strategy here is to use the most specific technique. This is implemented by storing domain information in an object hierarchy. Inheritance ensures that the most specific version overrides any defaults. Here's a graphical view of the domain hierarchy showing one of its associated properties. There are other hierarchies for types of algorithms and so on. Other kinds of choices, such as which algorithm type or grid size to use, involve trade-offs and can require more complex rules. We saw this example earlier in the choice about discretization method. In general, the decision rules may involve analysis of properties such as data flow, execution time, and space use, numerical accuracy, and numerical stability. Let me finish the discussion of implementation techniques by summarizing some alternative representation styles. One of the major trade-offs here is that more formality and structure in the representation can make system modification easier, but may slow down the construction of the actual system and the synthesis speed. A logic structure is one representation for a theory. Pre- and post-conditions and axioms provide the semantic constraints, with refinements derived by constructive proof and with the user or knowledge-based heuristics guiding the search. Abstract data types can also represent theories. Refinement results from instantiating the parameterized constructs of the theory. The type hierarchy, plus checking the constraints in the theory, supplies the choices of refinements. Correctness of the substitutions can be proved on the fly, derived as a legitimate view ahead of time, or collected up with other preconditions to be proved later. Object formalisms are another natural representation for domain theories. One design technique is to filter the problem description through a hierarchy that determines classification of its entities and selects a solution technique based on the classification. A more general but expensive technique is to represent goals and plans and selection criteria declaratively and build an interpreter. A streamlined alternative is to use a rule formalism to represent all three aspects. A rule has a trigger pattern to match against, which abstracts the selection criteria, applicability conditions to check semantic constraints, and a substitution pattern for the refinement. Especially at lower levels, it often makes sense to fold in the decision-making and consistency checking as part of the pattern match or applicability conditions. At higher levels, a series of decisions or metaprograms expressed in separate rules may better guide problem analysis and solution configuration. I hope you now have a feeling for how to represent the kind of information needed to synthesize a program from specifications. A small program synthesis system is no longer a PhD thesis, but simply a course project or part of research on the utility of a specific technique. There are many areas of ongoing research. I've already noticed the interest in search control, knowledge representation, and combining specifications and implementations for different domains. Other areas that I will touch on are knowledge-based evolution, program evolution, validation, programming environments, and user interfaces. Domain analysis and knowledge acquisition are very large active research areas. Ideally, end users should be able to add new knowledge to extend a system. Adding new objects at the same level is relatively straightforward if the interface is already sufficiently general. Changing the interface is much more difficult because it requires finding and modifying customers of the interface. Most difficult is changing the entire architecture. AI research has shown that tools specific to the domain, problem type, and representation can make it easier to modify the knowledge base. Program evolution requires iteration to produce a specification even before considering implementation, to modify the implementation because of performance problems, or to modify the specification because of experience with using the program. Specifications, therefore, should be living entities that can be easily understood and modified. To acquire a specification, you must have a good domain model. And in fact, some research concerns using the acquisition process to augment domain knowledge. Other research concerns specification validation using techniques such as paraphrasing, symbolic execution, and static analysis. Using an executable specification or default implementation as a prototype helps with analysis and debugging. And to support the process of modifying specifications, researchers are experimenting with specification editors and specification transformations. Initially, a record of design decisions and rationales is the output of specification and implementation. However, for succeeding cycles of evolution, it's also an input so that decisions don't have to be repeated. But there's a trade-off between regenerating the entire program and computing what part of the work can be reused. Reuse requires representation of the relationships between design decisions. When a change is made, we need to determine which decisions may no longer be valid and make hopefully minor modifications to resatisfy invalidated preconditions. Another issue is whether the final code correctly implements the specification. In general, formal verification is very difficult, and errors in the logical formulation are possible. A weaker but useful technique is to record all the assumptions made, not for proof, but so that if a problem is encountered, the assumption structure can be searched for the least supported links. Because users change specifications, and because applications such as those involving mathematical approximations do not have precise definitions of correctness, validation on sample problems will always be needed and is currently more practical than verification. For example, in mathematical applications, checking a few problems for which a closed-form solution is known against the approximations generated in the target code is quite valuable. The programming environment in which synthesis takes place is also a serious issue in making program synthesis real. On the one hand, a sophisticated environment with debuggers, traceability, and module interconnection checking facilitates the job of the developers. But if the environment is not commercially available on a variety of hardware, not maintained, or too expensive for the end users, the program synthesis system will not be used. I've said that end users should be able to determine the amount of automation that they want. This enables sophisticated users to make key decisions while enabling less experienced users to get the system to do some useful work for them. I found the following principles a practical guideline. Use domain terms for any questions brought to the user. Don't assume that the user understands all intermediate decisions made by the system, so relate the questions to the specification level to make them more intelligible. Avoid asking about trivial low-level decisions unless the user explicitly requests to make all choices. The system should have at least a minimal explanation of what the choices mean. And actually, research has indicated that building explainable systems leads to better designs. Also, the system should be prepared to make recommendations about decisions, but reserve ultimate veto power for the user. A simple form of mixed initiative dialogue will let the user specify answers in advance and initiate revisions. Fancy graphical interfaces are nice, but not often worth the time spent on them. Any new technology, whether lasers or expert systems, goes through stages from early research to widespread experimentation and identification of practical techniques to production. Program synthesis is in this middle stage. It's moved beyond computer science departments and into engineering departments and industrial research labs. Whereas early systems were generally written in Lisp, most current special purpose systems are in newer high-level symbolic manipulation languages such as Smalltalk, OPS5, or Mathematica, and are usually tens of thousands of lines of code. Also, a number of systems have been built on top of the refined system, which is hundreds of thousands of lines written in its own wide-spectrum language. Let's finish up with a look at a few samples of program synthesis to illustrate the range of approaches. For variety, I've omitted some of the most well-known research systems and focused on some of the newer applications. One extension to refine is the KID system, whose applications include algorithms for scheduling, sorting and searching, computational geometry, and linear programming. About 50 algorithms on the order of a few hundred lines have been synthesized from very short specifications of about 5 lines. The 20% of the KID's extension representing the domain theories is what makes the short specifications feasible. Most of the rest of the system is knowledge of basic algorithm schemas such as divide and conquer, global search, and local search, and knowledge of how to refine these algorithm schemas. Similarly, the Express project at Lockheed uses Refine to build target tracking systems and design fast Fourier transform algorithms. For example, from a description of the number of inputs to an FFT, the system has synthesized about 75 different highly efficient FFT programs, each of which is about 1,000 lines of Lisp or Ada code. Finite state simulators and other techniques such as temporal logics have been used for specification validation of telephone features in their implementations at locations such as Bell Labs and Ameritech. An early pioneer in program synthesis using multiple domains was the Draco system. Most of its applications were information management systems. In the same tradition, the Genesis system has recently shown the payoff of hard work in the area of domain analysis and application architecture. With the help of a user making some choices from menus, Genesis can synthesize customized database management systems of around 50,000 lines of C by combining fairly large-grained reusable modules. An example of the use of program synthesis for engineering is the ELF system for generating high-performance VLSI router algorithms. This OPS5 system produces programs of 1,000 or so lines of C from a specification of about 40 lines. One of the most recent trends has been the use of program synthesis for scientific applications such as mathematical modeling. Livermore's ALPAL and Purdue's LPAC are systems that generate code to solve practical problems involving integral differential equations. Specifications on the order of a page can lead to optimized code in the tens of pages, constructed primarily by synthesis in ALPAL and by selecting and combining library routines in LPAC. Rutgers Scene system has a similar purpose, but concentrates on immediate feedback via visualization and modification rather than optimization. The Synapse system follows this last trend in the generation of mathematical modeling programs. Some novel features are its use of symbolic manipulation system as an integral component and implementation language, and its use of the connection machine as one of several target architectures. So far, Synapse has proved useful at Schlumberger in generating a number of 3D finite difference programs that had never before been written and would have been extremely tedious and error-prone to generate by hand. As for program synthesis in general, the long-term future of the Synapse system remains to be demonstrated, but the future looks very bright.